Welcome back, children. Are you ready for today's class? Last class, we have started electric field. How will you define electric field intensity? The electric field intensity at a point in an electric field is defined as the force experienced by placing a unit positive charge at that point. And we learned electric field is a vector quantity. What was the direction of electric field for a positive charge? For a positive charge, it acts radially outward, away from the charge. For a negative charge, it acts radially inward, towards a negative charge. The equation for electric field was E equals F by Q. F by delta Q or F by Q. Today we learn properties of electric field lines. That's the main topic today we are learning. We can derive an equation for electric field due to a point charge. Electric field at a point due to a point charge. So we are deriving the equation. See, you consider a point charge. This is a point positive charge. This point is P, distance R. Electric field, since point positive charge, it is directed away. To find electric field, what we have to do? We have to bring a test charge and place here. Suppose the test charge I am placing here is Q0. Q0 is the test charge. This Q is the source charge. Now you can calculate the force between them. Imagine these are placed in vacuum. So let Q be the test charge. Sorry, source charge. Source charge. Q0 test charge. R distance from source charge to the test charge. Now, using Coulomb's law, you can calculate the force between these two charges. How will you calculate? What is the force equation? F equals K into Q into Q0 divided by R square. This is Coulomb's law, magnitude of force between these two charges. Now, you know the definition of electric field intensity. E is F by Q0. So what you will get? K, Q, Q0 by R square by Q0. So you are getting K, Q by R square. So this is the equation for the electric field intensity at a point due to a point charge. What is the equation? E is equal to K Q by R. This is the magnitude only. we can express in vector form. Since electric field is a vector, we need to express in vector form. The equation become E bar. Put a bar on the top. K Q by R square. And you have to write a R cap. What is R cap? It is a unit vector along the direction of R. R hat is unit vector along R. Okay. So this is the electric field equation in terms of vector notation in vector form. So E is inversely proportional to R square. In Coulomb's law also, you know, F is inversely proportional to R square. So if you plot a graph between electric field and R, how does it look? Electric field, E, R along x-axis, graph will be like this for constant charge. E proportional to 1 by R square. This is a graph between electric field and distance. This electric field, you cannot see it, right? We can experience, another charge can experience, right? We can visualize it by drawing. So I'm coming to the next topic, electric field line. What is electric field line? Or we call the lines of force, electric lines of force. What is it? See, you take a charge here, positive charge. Okay. If you move a 1 coulomb positive charge, what will happen? This will repel it away. Okay. If you leave the 1 coulomb charge, it will move away, right? It will move away. So there is a path traveled by this 1 coulomb charge. That path traveled is known as an electric line of force or an electric field line. So what is an electric field line? It is the path traveled by an independent unit positive charge in an electric field. Okay. It is the path traveled by an independent positive charge in an unit positive charge, means 1 coulomb charge in an electric field. This electric field lines can be straight or curved. If there is only one charge, 1 point positive charge, no other charges anywhere, then field lines will be straight lines. For an isolated positive or negative charge, the field lines will be straight lines. If there are more than one charges, the field lines will not be straight, it will be curves. Okay, so what is an electric field line? It is the path traveled by an independent unit positive charge in an electric field if it is free to move. Okay. What is the shape of the electric field lines? It can be straight lines or curves. When it will be straight lines, when charges isolated, for isolated positive charge, it will be straight line. For isolated negative charge, positive. Should be only one charge. But there are more than one charge, it will be curves. So what is an electric line of force or electric field line? An electric field line is the path traveled by an independent unit positive charge in an electric field. So these lines can be straight or continuous. I told you, for isolated charge, it will be straight lines. When you consider an isolated positive charge, the lines of force I am drawing, this will be the lines of force. These are straight lines. You have to draw straight lines. This is for an isolated positive charge. Q is greater than 0. Okay. Now, if it is an isolated negative charge, lines will be straight only, but the arrow mark should be toward the charge. So this is for isolated positive charge. For an isolated negative charge, lines of force will be towards it. Lines of force will be towards it. Straight lines. Okay. This is for isolated negative charge. We can write this as Q less than 0. But when there are more than one charge, lines of force will not be straight line. They may be curved. For a system of two positive charges, I am going to draw. See, this is a positive charge. This is another positive charge. Okay. So lines of force will be like this. So this is the lines of force due to an isolated positive charge. A system of positive, not isolated charge, a system of two positive charges. We can write here Q1, Q2 greater than 0. This is a system of two positive charges. If you draw for a system of two negative charges, it will be same, but arrows must be inward. Okay. So for a system of two isolated negative charge, negative charge, one negative, another negative. Same way you can draw. But arrow mark is towards the charge. Arrow mark must be towards the charges. So this is one negative, another negative. This arrow mark should be towards the negative charge. Okay, these are the different electric field lines for different charge configuration. So this one is isolated positive charge. This one is isolated negative charge. This is system of two positive charge. System of negative charge. Now, if there is one positive charge and a negative charge equal, such an arrangement is known as a dipole. We will discuss it later in detail. So you consider a positive charge and a negative charge, okay, with a small separation between them. One is positive, other is negative. Okay, this arrangement is known as dipole. For this, and drawing the field lines, positive, negative. So field lines will be like this, like this. For the negative charge, lines of force will be towards, positive charge away. So this is known as a dipole. So a dipole is a system of two equal and similar opposite charges separated by a small distance. We will discuss it later. Okay. So what is an electric line of force? It is the path traveled by a unit positive charge in an electric field if it is free to move. Okay. Then different types of lines of force around different types of charges I have drawn. Now, these lines of force have some important properties. These properties are very, very important for the examination point of view. Okay. Properties of electric field lines. That is our next topic. One, these electric field lines start from positive charge and end on negative charge. They start from positive charge and end on negative charge. Electric lines of force start from positive charge and end on negative charge. Second, they do not form closed loops. So they start at positive charge, end on negative charge, right? They do not form closed loops. They do not form closed loops because they have to end somewhere, right? Starting from positive charge, ending on negative charge. So they do not form closed loops. Do not form closed loops. Then another important property, electric field lines never intersect. Not two field lines intersect. What happens if they intersect? If they intersect at one point, then at that point there will be two directions for electric field. It is not possible. Electric field at one point can have only one direction. Electric field lines never intersect. If they intersect like this, at this point, there are two directions of electric field. It is not possible. What is the reason? If electric field lines intersect at one point, there will be two directions for the electric field at that point, which is not possible. Two directions for the electric field at that point, which is not possible. Then, third property, see, I told you electric field lines are, sometimes it is curved and can be straight lines. Curved when more charges are there, right? For isolated charge, point charge, positive charge, straight lines. So, at any point on the line of force, the direction of electric field is along the tangent drawn at that point. So, the direction of electric field is along the tangent drawn at that point. So see, suppose this is a line of force. So at this point, electric field is along this tangent. At this point, electric field is along this tangent. Okay, that will be along the tangent. At this point, electric field is along this tangent. That is another important property. Then, electric field lines are normal to the surface of a conductor. The reason for this we will cover later only. Okay, now we are not in a position to answer the reason of this property. Electric field lines are perpendicular to the surface of a conductor. The reason we will learn towards the end of this No, next lesson only we will learn. What is lesson? Okay. Electric, now you learn the property. Electric field lines are perpendicular to the surface of a conductor. Then electric field lines do not pass through a conductor because inside the conductor electric field is zero. Charges only are situated on the surface of a conductor. Inside no charge is present. So electric field inside the conductor is zero. So electric field lines do not pass through a conductor. Electric field lines do not pass through a conductor. Electric field lines do not pass through a conductor. What is the reason? Because electric fields inside the conductor is zero. No electric field inside the conductor. Charges only lie on the surface. Now another property, electric field lines are crowded in the regions of stronger field. When the field is stronger, field lines are crowded. Okay, these are the properties of electric field lines. I will tell once again. Electric lines of force start from positive charge, end on negative charge. Electric field lines do not form closed loops. Electric field lines never intersect. What will happen if they intersect? Something happens? Yes. If they intersect, it means that there are two directions for electric field at that point. At one point, there can be only one direction for the electric field. Okay. So they cannot intersect. Then, how will you find out the direction of the electric field on a line of force? The direction of electric field is along the tangent drawn at that point. So when you take a line of force, maybe curved, electric field directions will be different at different points. It will always be at any point, electric field direction is along the tangent drawn at that point. Electric field lines are perpendicular to the surface of a conductor. Then electric field lines do not pass through a conductor. Why? Inside a conductor, no charges are residing. Okay. Excess charges will be only on the surface of the conductor. So electric field inside the conductor is zero. Electric field lines are crowded in the regions of stronger fields. So we learned the equation for electric field at a point due to a point charge. What is the equation? Electric field at a point due to a point charge. What was the equation? E is equal to KQ by R square. Now we can do one numerical based on this electric field. One more property I have to tell you. One more property of electric lines of force. Electric field lines are continuous curves without any breaks. There cannot be break on the electric field lines. They are continuous curves without having any breaks. If there is a break, that means there is no electric field at that point. Wherever electric field, there will be lines of force. If electric field is not there, there will be no lines of force. So electric field lines are continuous curves, okay, without any break. Okay, what is the reason? If they have break, that means electric field is absent at that point. So it is not possible. Electric field lines cannot have continuous. Electric field lines cannot have sudden break. They are continuous curves. So we will do one question, question number 1.8 from the textbook. Two-point charges. So electric properties of electric field lines. I told you why two lines of force never intersect. If they intersect, there will be two directions for electric field at that point, which is not possible. It can be asked for short questions. That's why I repeated again. Okay. Then electric field lines cannot have sudden breaks. They are continuous curves. What is the reason? If they have sudden break, what would it mean? Break means there is no electric field at that point. So there won't be any line of force. So it is not possible. So we can do this question. Question number 1.8. 2-point charges, 3 microcoulomb and -3 microcoulomb are located 20 centimeter apart. What is the electric field at the midpoint of the line joining the two charges? See, two charges, QA, another charge, QB. Distance between them, 20 centimeter. You need to find out electric field at the midpoint. See, this is the midpoint. This distance from one charge is 10. So, see, at the point, the midpoint O, electric field due to positive charge is away from the point charge. So due to the charge QA, electric field is in this way. So I am writing EA. And QB is negative, right? -3 into 3 microcoulomb. QA was 3 microcoulomb. So negative charge field is towards it, from O towards the negative charge. So in this direction. So both the fields are in the same direction. So they add up, simple. Okay. So what will happen to the total electric field? EA plus EB, they add together. Why? Direction is same. We learned for negative charge, field is towards it, directed towards it. Positive charge, directed away from it. So at the point O, both the fields are along the same direction. So you just add it. Okay. So you know and both these fields are same because charge magnitude is same, distance also same. So you can write KQA by R square plus KQA by QB by R square. Magnitudes of the charges are same. So 2KQ by R square. 2 into K value, you know, 9 into 10 raised to 9. Q is given. What is that? 3 microcoulomb. 3 into 10 raised to minus 6 by R. What is distance from one charge to the point or center? 10. 10 into 10 raised to minus 2 square. So this is the equation for this is the electric field. Just you have to calculate it. So E will be how you are getting 2 into 9, 18. 18 into 3, 54. So 54 into 10 raised to 9 minus 6 is 3. Then 10 raised to 4. So what will be the answer? This will be 10 square. 10 square into 10 raised to minus 4. So 10 raised to minus 2. So it will come to the 11. So 5.4 into 54 into 10 raised to 5. What is the unit? Newton per coulomb. It is 5.4 into 10 raised to 4 Newton per coulomb. This is the electric field. Now you have to find out B part. If negative test charge of magnitude 1.5 into 10 raised to minus 9 is placed at this point, what is the force? So what is the force equation? You know E is equal to F by Q0. Here test charge is given. Test charge is 1.5 into 10 raised to minus 9. So we can write force is Q0 into E. Q0 1.5 into 10 raised to minus 9 into E. What is E? You calculated 1.4 into 10 raised to 4. So this will be the answer. So 8.1. 8.1 into 10 to the power minus 5 Newton. Okay, children. So this is about the electric field lines of force. So today we will stop the class. We will see in the next class. Bye bye.